Today we're going to start to talk about panel data models. So let me change some of the options here. Yeah, so let me see if that helps. So today's topic in the computer. It's kind of slow, so let's give it some time. Okay, so let me see. Okay, so today's topic is panel data models. So we're going to start with the basic model that describes what do we mean by panel data, and you should all be aware with that. But basically, it's a model where we have data on specific units. So the I correspond to a unit. So remember, when we say one unit, so we refer to an individual, but it could also be like a country. And we observe this individual or this country, this unit of observation, several time periods. Okay, so we have these two dimensions. So as I say in my undergraduate class, so usually panel data model, you have data on multiple individuals during multiple time periods. So that's kind of what defines panel data. So of course we also have data on vector of explanatory variables that are time variant. So these explanatory variables change through time. So this is what are called time variant explanatory variables. And we also have a vector of time invariant explanatory variables that are also taught to, well, so this is a tilde, this is not a hat. This is a vector of coefficients, and I use that, tilde to differentiate it from another coefficient that we're going to be using. Later on. So this time variant explanatory variables this exclude the intercept in this basic model. And for example, if we're thinking about households, an example of a time variant explanatory variable might be income. Okay, it's common that income changes through time. Zi, on the other hand, as I was telling you, so it's a vector of time invariant factors. So vector of time invariant factors. If we're thinking in terms of the household level, a good example would be, race. Okay, and I didn't give a specific example of a specific outcome, but an outcome might be health. So, let's say you are interested in looking how health of different households changes through time, as explained by some time variant explanatory variables, such as income, and some vector of time invariant factors such as race. So that's kind of the context, and then we have our error term. Now generally the objective, so generally in most cases, the objective of the analysis is that, vector beta, vector coefficients beta, okay, which is the effect of that vector of explanatory of time variant variables on the average value of our dependent variable. Okay, so that tends to be the focus of the analysis. Only once in a while we're interested in the effect of time invariant factors, but it's possible. But most of the time, our interest is the time, the effect of these time variant explanatory variables, and that's, it's going to be the focus of our analysis and the focus of our the presentation of the methods and procedures and the equations. So when we talk about panel data, there are the three most common model structures. So there are some others, but these are the most common and the basic ones, I will argue. It's common and basic model structures. And today, we're going to define each of these structures. Okay. So the first one is going to be what's called the pool regression model. The second is going to be what's called the fixed effects model. And this model structure refers to what do we believe is the model underlying the data that we have at hand. Number 3 is what's called the random effects model. Okay, so a key element of analysis with panel data is the identification of what is the model structure. The model structure that we have, and that's kind of the emphasis. So there are going to be two components here: the identification of the model, okay, of the panel data model, the structure, and the other one is going to be estimation. And they are related to each other, but it's important, and I'm telling you this, from now on. The first thing that you need to understand, and we need to understand very well, is what's the model, the underlying model that we have at hand. And the other part is going to be the estimation procedures. Sometimes those two things can be confused. So have that in mind. So let's go model by model. So let's start with the pool regression model. Okay, and this is kind of like the basic pool regression model. So again, we're going to write it the way that we wrote it before. Okay, so notice that now we don't have that vector z. So let's assume in this model, in this presentation of the model, is that the effect of those time. So these are, remember, so these are the time invariant factors are kind of summarized in that alpha intercept that we have here. So kind of like an underlying option here is that there is no heterogeneity across the individuals, and this is when we're talking about heterogeneity is there is no heterogeneity related to this time invariant factors across individuals. So there is no heterogeneity related to time invariant factors, okay, across individuals. So that's kind of like underlying assumption here. Okay, so, and I'm saying that this is kind of like a basic model because later on when we go to the lab, you will see that actually in random effects model, in the pool regression model, we can include and we can estimate the effects of certain time invariant factors. Okay, so here the way to think about this model, one way to think about this model, you have this context where actually you do not observe any time invariant factor. Okay, so they are all unobserved. Okay, so that's kind of like this general context. But in reality, later on, we're kind of going to relax that assumption when we're looking in practice. But, to understand the model, it's okay with this assumption. With, again, basically here, an underlying assumption is that all these factors are unobserved. Zi's are unobserved factors. Okay, again, that can be relaxed, but for now, it's okay. So I think that you get all the intuition using this simple model. Okay, so in this model, there is no heterogeneity related to time invariant factors across individuals. Now, let's look at the second model, which is the fixed effects model. Okay, so we have this model, we have y at t equal to alpha I plus xit prime beta plus t. Okay, so notice here the difference between this fixed effects model and the pool regression model is that now alpha I is one intercept. Basically, this is what we have here in this model. It's like having one intercept for each individual. And again, I use individuals since most of the time when I've done panel data, I have had data on individuals, but it could be an observational unit. It could be like a country or a county or a state that's observed through time, but I'm going to be calling it individual. So basically here, the difference between the previous model, the pool regression model, and this fixed effects model is the fact that now we have like one intercept for each individual, and before basically we were assuming that, that intercept was a constant. So there was not heterogeneity related to these time invariant factors. So again, if we go back to the notation that we had previously, so basically now we're assuming is that effect of that vector of unobserved time invariant factors changes from individual to individual. A key assumption in this model, so this model assumes that there is zi's, remember these unobserved time invariant factors, zi. So remember these are unobserved time invariant factors. are correlated. So that's a key assumption of this model. Are correlated with XIT. Okay, so this is a key assumption of the model. And again, later on we'll talk about the advantages. But this goes back to our discussion of endogeneity. So if you remember, I mean, basically, one way to think about endogeneity is when your explanatory variables are correlated with the error term. So, and this idea it comes back into play here, in this model. So have that in mind. So that's gonna make this fixed effects model kind of like robust to certain forms of endogeneity. Okay, so now let's look at the random effects model. Okay. So again, let's write it down. Our basic model. Now we have an intercept, as in the case of the pool model. But we're also going to have two error terms. Okay? So what we have, what's new here, is that this mu I these are individual specific random effect. Okay, or another way to think about that's like an individual specific error. So it's kind of like an error that applies to each individual in particular. So that's kind of like a different way to think about heterogeneity. Okay, so before, remember the way that we were kind of modeling this heterogeneity was through kind of this intercept that's in the fixed effects model, and now in this random effects model, the way that we're modeling this heterogeneity is through like an additional error term that is unique to each individual. Now, an assumption, the other difference is the assumption regarding the correlation between those unobserved invariant factors and the explanatory variables. So in the random effects model, the assumption here is assume that these unobserved factors, so assume that Zi is unobserved, but uncorrelated with explanatory variables. Okay, remember, and now here the assumption regarding Zi hat alpha. So here basically we're assuming that that's equal to the constant plus that individual specific error. Okay, so as you can see, it's a different way to account for this effect of these unobserved time invariant explanatory variables. So that's something that you're going to have to learn to differentiate. Okay, so going back, so we have started to talk about panel data models. So we introduced the basic model, and then we talk about the three main structures: the pool regression model, where we assume that we have a constant intercept, so there is no heterogeneity related to these time invariant factors across individuals. So these unobserved factors. In the fixed effects model, the way that we account for that endogeneity is through an individual intercept for each individual. A key assumption here is that the explanatory variables can be correlated with these unobserved time invariant factors. in the random effects model, what we assume is that these time invariant factors are uncorrelated with explanatory variables, and the way that we account for endogeneity is through the inclusion of an additional error term that is individual specific. Okay, so that's kind of like a general overview of the three type of models that we are going to be discussing. So let's go and talk a little bit more. So now what we're going to be doing is we're going to be talking in detail about each model, the general assumptions regarding each of these models, and then we'll talk about the estimators that you can use for each model. So let's start the discussion with the pool model. So sometimes this model is called population average model. Yeah, so going back, so remember we have this model, one intercept, R vector of time variant variables. So I, the number of individuals, goes from 1 to n. T, go from 1 to t. Now, so here what we're going to be doing is actually goes from ti. So basically what we're allowing here is for each individual, we're allowing for potentially having different individuals observe different number of time periods. Okay, so for individual you might observe only one time period, for another you might observe 5, for another you might observe 10, and so on and so forth. So actually if ti actually is a constant for all I, which basically means that all the individuals are observed the same number of time periods, so then we have what's called a balance panel. Okay. If on the other hand, if ti is different to a constant, which again here we're allowing the potential for different individuals to be observed a different number of time periods. So then we have what's called like an unbalanced span. Okay, so to simplify things, initially, we're only going to be considering the estimation of balance panel. I mean, you get most of the intuition by using that. There are some things that you need to have to take into consideration when you don't have an unbalanced panel. But most of the time, that type of things, I mean, the software, when you are estimated, allows you to take into account those issues. But most of the intuition and the theoretical understanding of the issues are gained by just using balance panel without having to complicate things. Okay, so what are the assumptions for the basic model? So the assumptions for the basic model is that everything is kind of nice. So the first thing is going to be the exogeneity assumption. So that initially at least we don't have to deal with all these problems, and we can just focus on how do we account for these different type of models, their error structure. So we'll be assuming that all of the explanatory variables are exogenous. Okay, so that's why we're saying that. We're going to be assuming homoscedasticity, so the variance of the errors. constant. Okay. So this is homoscedasticity. So now something that I haven't mentioned here for both exogeneity and homoscedasticity, notice that there is no correlation between the error term for an individual and time period t and the explanatory variables in all the time periods for that individual I. And for homoscedasticity, it's the same thing. The variance of the errors is not a function of the explanatory variables on any of the time periods. So that's kind of like a stronger forms of exogeneity and homoscedasticity that we were used that we used before, where when we're talking about cross-sectional data. And regarding the covariance, so we have the covariance, and I'll explain what's going on here. So for individual I, we have two individuals, an individual I and an individual J, and we're considered these individuals being observed in time period T and time period S, respectively. So then we need to take into account the error terms of this individual J and all the time periods, I and J and all the time periods. So this is if I is different than J, or T is different than S. So basically here, what the thing is telling us is that there is no correlation between individuals. No correlation between individuals. Okay, so that's for the I different than J. So if we have observations of different individuals, they are not correlated, the covariance is equal to 0. And if we have the same individual, but if we observe this individual, there's different time periods, so at least originally, we're assuming that there is no autocorrelation. So there is no okay. So two things going on here. The errors for different individuals are not correlated, so they are independent. I mean, that usually happens if we have a random sample. Different individuals are not correlated. The errors are not correlated. And the other one has to do with observations for the same individual across different time periods. So here, at least initially, we're assuming that those observations are also independent. Again, so this is kind of like a basic model. Several of these things can be relaxed. You can have a pool regression model with endogeneity. Of course, you can have a pool regression model with heteroscedasticity. And also you can have a pool regression model where you might have some sort of correlation between individuals and even autocorrelation. Okay, so, but initially we're gonna be assuming this model will basically everything kind of looks nice regarding the errors. Okay, so this is the pool model. Those are gonna be the assumptions, and now we're gonna be talking about the estimators, and that's probably gonna be the topic of the next class. Okay, so estimators. This is gonna be for the pool model. Okay, and we will discuss. We're gonna be discussing actually. We're gonna be talking about 5 estimators. So the first estimator we will talk about is what's called pool OLS. The second estimator is what's called the between estimator. For the pool model. So here, I'm going to use PM for the pool model. The third estimator is what's called the within estimator, or sometimes called or fixed effects estimator. Estimator for the pool model. Then we'll talk about the first difference estimator. For the pool model. And finally, we'll talk about the random effects estimator for the pool model. Estimator for the pool model. Okay, so now remember, and I'm letting you know this thing in advance, because as you can see, some of the estimators have the same name as the model structure that we had mentioned before. So remember, one thing is going to be the model and another thing is going to be the estimator. So of course, for the pool model, we're going to have this that's called pool OLS, but also, we're going to be we're also going to have something that's called fixed effects estimator. But this is the fixed effects estimator for the pool model. And then we'll also be talking about this random effects estimator for the pool model, in addition to this between estimator and also this first difference estimator. So that's kind of what I talked about before, that from the beginning, you need to be careful about the language and the terminology to avoid getting confused about it. Okay, so today, we talk about this introduction of panel data models, the main model structures, and we started to talk about this pool model in detail, the assumptions for the errors, and then I have listed the 5 estimators that we're going to be using for the pool model. As you can see later on, actually, these estimators are very straightforward. All of these estimators are going to involve ordinary least squares. So basically, everything that we learn basically is going to be applied. In terms of estimation procedures, there are not that many new things here. You are going to see again that once again, most of these estimators, they are just mainly OLS. The random effects estimator is a generalized, generalized linear regression estimator, generalized least squares estimator, and the other issue would be how we can potentially account for heteroscedasticity and autocorrelation, and for that you will see how we can use some form of heteroscedastic autocorrelation consistent covariance metrics. So these estimators are not gonna be that difficult. And probably most of the confusion has to do with the names. But actually, in terms of estimation, with what we know, with what we learn in this class and probably your previous econometric classes, it's very easy to understand what's going on. Okay, so we'll continue next time with more details about these estimators for the pool model.